When we talk about waves in the ocean, we are not talking about water moving from one place to another in the way a current does. We're talking about how energy, introduced at the air to sea interface, is transmitted through seawater in an organized and predictable way. Waves are one of the primary mechanisms by which the atmosphere communicates energy to the ocean and ultimately to the coastlines. This distinction matters because many of the physical processes we care about near shore, like sediment transport, shoreline erosion, mixing in shallow habitats, and even aspects of coastal ecology, are controlled not by how much water is moving, but how much wave energy is transformed as it travels, slows down, steepens, and dissipates. Today's goal is to understand waves as a physical system. What are they? How they are generated? How they move energy without transporting mass? And why their interaction and the sea floor fundamentally changes their behavior. That framework will carry directly into our next lectures on tides, currents, and shoreline processes. When students first encounter waves, the most persistent misconception is the waves are water moving forward. That intuition comes from what we see at the shoreline, where waves clearly crash and push water landward. But in the open ocean, and physically speaking, a wave is best understood as energy propagating through a medium, not mass transport of the medium itself. At the air to sea interface, wind transfers energy into the ocean surface. That energy does not cause a slab of water to slide forward. Instead, it causes individual water parcels to oscillate around a stable position. The wave we observe, the crest and the trough pattern, is the spatial expression of that oscillatory motion. Take a look at the image on the right side of the slide. The yellow dots represent a particular water molecule. Notice the top row at the surface. The wave makes it appear that water is moving from left to right, but the reality is that a particular molecule of water is simply moving in a circle. So when a wave passes through, water is not actually traveling very far. It is simply the energy that is moving. If I may get a little ahead of myself here, notice how the circles of rotation are getting smaller with depth. The highest energy level is at the surface, and then it decreases as you get deeper and deeper. So water molecules toward the bottom are making much smaller circles than the ones at the top. We will come back to that in a few moments. Crucially, waves exist because the ocean surface is constantly trying to return to equilibrium. Gravity pulls elevated water back down. Surface tension acts to smooth out that curvature. These are called restoring forces, and the balance between the energy input and these restoring forces determine the wave shape, the wave speed, and ultimately the wave's behavior. This framing matters because it separates waves conceptually from currents. Currents are bulk water movement driven by sustained forces like wind stress and density gradients. We'll talk about those in a future lecture. Waves, in contrast, are transient energy signals that pass through the water. That distinction will be essential when we later discuss tides and circulation. To explain how waves behave, we need a shared vocabulary. Wavelength is the horizontal distance between two crests. Wave height is the vertical distance from trough to crest. Wave period is the time it takes for one wave crest to pass a fixed point. And frequency is simply the inverse of that wave period. Among these, wave period is especially important. The period is established when the wave is first generated, and that is done by the wind conditions such as wind speed, wind duration, and the wind fetch. And the period remains remarkably stable as the wave propagates across the ocean. Even when wave height decreases due to energy loss, the period is largely conserved. Wave speed links space and time. How fast a waveform moves across the surface. In deep water, wave speed depends primarily on the wavelength and not the height. Long wavelength waves travel faster than short wavelength waves. This is why distant storms can send long period swells racing across entire ocean basins. This matters physically because period and wavelength encode information about the energy source. A beach receiving long period swells is experiencing energy that may have originated thousands of kilometers away, even if local winds are calm. If we could track a single water parcel beneath a passing wave, we would see something surprising. The parcel does not travel forward with the wave. Instead, it moves in a closed, nearly circular orbit. Upward and forward under the crest, downward and backward under the trough. At the surface, these orbits are largest. With increasing depth, orbital motion decreases exponentially. By a depth of roughly one-half the wavelength, wave-induced motion is negligible. This depth dependence explains why surface waves can pass over deep-sea ecosystems without disturbing them. This orbital motion is why waves can transmit energy across ocean basins without transporting water mass. It also explains why floating objects bob up and down rather than being carried rapidly forward. Unless additional forces such as wind drag or braking intervene. This framework will later help us understand how waves interact with the sea floor near shore, where the bottom interferes with orbital motion and fundamentally alters wave behavior. Wave generation begins with wind blowing across a smooth ocean surface. Even tiny surface irregularities create pressure differences between the windward and the leeward sides of these bumps. The wind pushes more strongly on the upwind face, transferring that momentum to the water. As these ripples grow, they present a larger surface to the wind, and that increases energy transfer even more. This positive feedback continues until limiting factors such as wave breaking or changes in wind conditions halt their growth even further. These variables control how large waves can become: wind speed, wind duration, and fetch, which is the distance over which the wind blows in a constant, uninterrupted direction. Wind duration is the length of time that wind blows. Strong winds over short fetch produce smaller waves than moderate winds sustained over long fetch. Importantly, once waves leave the generating area, they no longer depend on the wind that created them. They propagate freely as a swell, carrying information about their source conditions encoded in their period and wavelength. The distinction between deep and shallow water waves is often misunderstood. It has nothing to do with absolute depth. Instead, it depends on whether wave-induced orbital motion interacts with the sea floor. In deep water, orbital motion decays before reaching the bottom, and waves behave as if the ocean were infinitely deep. In shallow water, the bottom interferes with orbital motion, flattening the orbits and forcing water parcels into more horizontal movement. The wave base in this figure illustrates the depth at which there is no more orbital motion. In other words, the water under the wave base is not impacted at all by the wave. Notice in the illustration what happens when the wave begins making contact with the ocean floor. A close look at the orbitals on the diagram will show the orbitals are flattening into more of a flat oval instead of a circle. Pause the video at this point to look carefully at this illustration. When the wave touches the seafloor, the interaction will slow the wave, shorten its wavelength, and increase wave height as energy is compressed into a smaller horizontal space. The wave is not gaining energy, it is being reshaped by boundary constraints. This transition sets the stage for wave breaking and for the transfer of wave energy into coastal processes such as sediment transport and shoreline erosion. As a wave enters shallow water, frictional interaction with the bottom slows the lower portion of the wave first. Because the wave period remains fixed, as we previously talked about, a decrease in speed forces a decrease in wave length. Energy conservation is key here. The wave is carrying the same amount of energy it had offshore, but now that energy is distributed over a shorter horizontal distance. The result is increased wave height and steepness, as you can see in the illustration here. This process, called shoaling, is why waves become larger near the shore even though no additional energy is being added. It is a geometric and dynamical consequence of boundary interaction. Understanding shoaling is essential for predicting coastal wave climates and for explaining why certain coastlines experience intense wave energy despite being far from storm centers. Wave breaking represents a fundamental transition. Organized wave motion collapses into chaotic turbulence. This occurs when the crest moves faster than the wave base can support, causing the crest to topple forward. Breaking is not merely dramatic, it is the primary mechanism by which wave energy is dissipated in the coastal ocean. The energy that once traveled as coherent wave motion is converted into turbulence, mixing, sound, and even heat. Different types of breaking reflect differences in bottom slope and wave conditions. Gentle slopes favor what we call spilling breakers, while steep slopes produce plunging breakers. Spilling waves break over a longer distance, and that spreads out the dissipation of energy. They are generally considered low energy because the wave gently breaks without significant force on the shoreline. Whereas plunging waves, on the other hand, form steep crests and often forms tubes or barrels as they break. They often release a lot of energy and make explosive sounds. Those differences strongly influence sediment transport and coastal morphology. So up to this point, we have treated waves primarily as a physical phenomenon occurring at the ocean surface, generated by wind, shaped by water depth, and ultimately dissipated through breaking. On this slide, I want to reframe waves in a more systems-level way. Waves are the dominant mechanism by which energy from the open ocean is delivered to the coastlines. Almost everything that happens physically at the shoreline begins with waves. When waves approach the coast, they are carrying energy that was originally transferred from the atmosphere, often far from shore. That energy does not simply disappear when the wave breaks. Instead, it is converted into turbulence, water motion, and shear stresses that act directly on the sediments in coastal landforms. This is why coastlines are dynamic environments rather than static boundaries. They are consistently being worked on by incoming wave energy. One of the most important consequences of wave energy delivery is sediment mobilization. Breaking waves stir up bottom sediments, lifting sand and finer particles into the water column. Once sediments are suspended, they can be transported by currents generated within the surf zone. The amount of sediment moved and the size of particles that can be moved depends entirely on that wave energy. Higher energy wave conditions can mobilize coarser sediments and reshape the sea floor more dramatically than low energy conditions. The angle at which waves approach the shoreline is especially important. When waves arrive straight on, their energy is distributed symmetrically, and sediment movement tends to be primarily onshore and offshore. However, when waves approach at an angle, which is the most common case, they generate a net current that flows parallel to the shoreline. This longshore current transports sediment laterally, redistributing sand along the coast. Over time, this process shapes the beaches, the spits, the barrier islands, and the sandbars. What matters here is that waves themselves are not carrying sediment long distances. Instead, waves provide the energy that enables sediment transport by nearshore currents. This distinction mirrors what we discussed earlier about waves transporting energy rather than mass. The wave delivers energy, the water responds by moving sediment. From a broader perspective, this is why coastlines respond so strongly to changes in wave climate. A shift in dominant wave direction, an increase in storm intensity, or a change in a wave period can alter erosion and deposition patterns even if sea level remains constant. Coastlines are therefore sensitive indicators of changes in atmospheric forcing. So this framing also sets up the next parts of this course. when we later examine shoreline processes in coastal habitats, we will repeatedly come back to wave energy as a controlling variable. Whether we're talking about sandy beaches, rocky shorelines, seagrass beds, or even coral reefs, the physical environment, and therefore the biological environment, is structured by how wave energy is delivered, transformed, and dissipated. Up to this point, we have focused on waves generated by wind acting at the ocean surface. Tsunamis allow us to expand that framework by asking a deeper question. What happens when energy is introduced not at the surface but at the sea floor? The answer is a wave that behaves very differently from the wind waves we usually see, but that is governed by the same physical principles. A tsunami is a gravity wave, meaning its motion is restored by gravity acting on displaced water. What makes tsunamis unique is how they are generated. Instead of wind transferring energy gradually to the surface, a tsunami begins with a rapid vertical displacement of the sea floor, most commonly along a fault line during a large earthquake. When the seafloor moves upward or downward, it pushes or pulls on the entire column of water above it. This sudden displacement injects energy directly into the ocean. Because the water column is displaced from bottom to surface, the resulting wave has an extraordinarily long wavelength, often on the order of tens to hundreds of kilometers. The wave height in the open ocean may be very small, sometimes even less than a meter. But the key point is that the wave involves motion of an entire water column, not just the surface. This leads to one of the most important physical characteristics of tsunamis. They behave as a shallow water wave everywhere, even in the deep ocean. Earlier in this lecture, we defined shallow water waves as waves whose orbital motion reaches the seafloor. For tsunamis, the wavelength is so long that the condition is met across the entire ocean basins. As a result, tsunami speed depends on water depth and not wavelength. And tsunamis can travel across oceans at jetliner speeds. Despite their speed and energy, tsunamis are often barely noticeable in deep water. Ships at sea may pass over them without detecting anything unusual. This reinforces a core idea we introduced earlier. Wave energy does not necessarily correspond to visible wave height. In the case of tsunamis, the energy is distributed across an enormous horizontal distance, producing a low amplitude but highly coherent wave. The behavior of tsunamis changes dramatically as they approach shallow coastal waters. As depth decreases, wave speed slows, wavelength shortens, and wave height increases. Exactly the shoaling process we discussed earlier. The tsunami does not gain energy near shore. Instead, the same energy is compressed into a smaller spatial region, leading to dramatic increases in wave height and force. From a wave physics perspective, the tsunamis provide a powerful example of how generation mechanism, wavelength, and boundary interaction determine wave behavior. They are not an exception to wave theory, they are an extreme case that helps clarify it. Understanding tsunamis as waves, not as some anomaly, strengthens our ability to understand tides, coastal processes, and the broader dynamics of ocean motion. These are images from a tsunami that hit Indonesia in 2004. The wave reached 51 meters in height in some places as it came to shore, and it resulted in over 117,000 deaths. The tsunami was triggered by a massive 9.3 magnitude underwater earthquake about 100 miles from Sumatra and about 20 kilometers in depth, or about 12 miles deep. So that wave was 12 miles deep. At this point, it should be clear that waves are not just a surface feature of the ocean, they are a fundamental component of how the ocean system functions. Waves represent one of the primary pathways by which atmospheric energy enters the ocean, and they determine how that energy is redistributed, transformed, and ultimately dissipated. One of the most important roles waves play is in regulating near-surface and near-shore mixing. Even though waves do not transport water mass over long distances, the turbulence generated by wave motion, especially during breaking, enhances mixing in the upper ocean and in shallow coastal environments. This mixing affects temperature structure, gas exchange, and the distribution of nutrients and suspended particles. In other words, waves help control the physical environment that marine organisms actually experience. Waves also strongly influence sediment dynamics, which in turn structure benthic habitats. By mobilizing sediments, waves determine whether a seafloor is rocky or sandy, stable or frequently disturbed. These physical environments place strong constraints on which organisms can live there. For example, organisms adapted to high-energy wave environments tend to be firmly attached, flexible, or able to burrow quickly, while low-energy environments favor different life history strategies. Thus, wave energy indirectly shapes biological communities by controlling habitat stability and substrate type. From a systems perspective, waves act as a translator between atmospheric processes and coastal and benthic systems. Winds do not directly erode shorelines or resuspend sediments. Waves do. That means that changes in atmospheric forcing, such as shifts in storm frequency or wind direction or wind intensity, are felt more immediately in the ocean through changes in wave climate. The physical signal of climate variability often arrives at coastlines in the form of altered wave energy. It is also important to recognize that waves operate across a wide range of spatial and temporal scales. Short period wind waves affect daily conditions on beaches and reefs, while long period swell can deliver energy across entire ocean basins. Both scales matter, and both influence coastal systems in different ways. This multi-scale nature of wave processes is something we will return to repeatedly as we expand our view of ocean motion. And finally, waves provide an essential conceptual bridge to the rest of this unit. Tides, which we will examine next, can be understood as extremely long wavelength waves driven by gravitational forcing rather than wind. Surface currents, in contrast, involve sustained forces that produce net water transport rather than oscillatory motion that we see here in waves. By clearly understanding what waves are and what they are not, you now have a reference point that will help you distinguish among these different modes of ocean motion as the course progresses. In the next lecture, we will revisit the wave framework you now understand and apply it to tides. Tides are not a separate phenomenon. They are very long wavelength, long period waves forced by gravitational interactions. After tides, we will shift to surface currents where sustained forcing produces net water transport rather than oscillatory motion. By keeping these distinctions clear, you'll be able to interpret ocean motion across a wide range of spatial and temporal scales.